All right, well then I'm going to turn it over to my colleagues in ocean engineering and let them get started. So you should be able to just do here or the map.
Hi everyone, my name is Dr. Christine Gilbert. I'm an associate professor in aerospace and ocean engineering, and I'm here to talk to you tonight about ocean engineering program. Does anyone know what ocean engineering is? No? Has anyone ever been on a boat? Yeah? Who likes going on boats? Fast boats, slow boats, big boats, small boats? Yeah, I love all boats, right? I am working in the ocean engineering program because I actually loved to watch the waves break at the ocean when I would go to the beach when I was a kid. I also really like to watch the wakes that are formed by boats as well. Okay, so what is ocean engineering? Ocean engineering is the design of ocean vehicles and structures, ships, boats, submarines, autonomous vehicles, offshore structures. So one of the things that I think is a common misconception is that a lot of different schools call some of these programs by different names. So for example, Michigan has a naval architecture and marine engineering program. What we learned in our ocean engineering program here at Virginia Tech is very similar, right? It provides you with the same kind of background to work at a place like the Naval Surface Warfare Center, design next generation of ships, submarines, aircraft carriers, and so on. The one reason why we chose ocean engineering is we wanted to broaden that and not restrict everything just to boats, ships, and submarines, but we wanted to also include offshore structures or undersea laboratory type things. 90% of goods are transported by ships. Ships are actually, especially the very large ones, are the largest human-made vehicles, so bigger than airplanes, bigger than spacecraft. The marine renewable energy sort of is giving us 2,300 terawatts power per year, and the U.S. Navy budget in fiscal year 2022 was $212 billion. So there's actually a lot of opportunities within this field. One of the other things to note here is there's a Navy lab called the Naval Surface Warfare Center, Carter Rock, which is in West Bethesda, Maryland. They do a lot of design for the Navy's ships, destroyers, aircraft carriers, and so on. One of the things that they have been telling us recently is that they really have a high demand for the next generation of designers for these ships, aircraft carriers, and so on, because most of the current designers right now are about to retire, and there's no clear path for people coming up to take those jobs. So if you're interested in designing ships, this is a really good opportunity for you. So what do you learn in our major? You learn a lot of things. You learn fluids, you learn about structures, vehicle dynamics, controls, software like CAD, CFD, finite element analysis, as well as laboratory skills. One of the things that's really unique is, you might say, oh, I want to major in mechanical engineering because it's very broad. And that's actually what I thought when I was a freshman. And that is actually what I majored in. I got my bachelor's, my master's, and my PhD all in mechanical engineering. But then because of my love of the ocean and my love of waves and my love of boats, I ended up having to kind of switch gears after I got my PhD, and I had to kind of learn this whole new set of nomenclature. And it would have been really cool if my capstone design had involved me, designing a full ship with a group of my peers instead of, designing, we designed some kind of swim equipment or something for my senior design. So one of the things that's really unique about this is that you could basically design a complete ship in your capstone design, or a submarine, or an offshore structure. We also learn about things like hull forms, stability, hydrodynamics, structures, materials, propulsion, vehicle dynamics, and oceanography. And there's this nice picture in the lower right-hand corner showing the wake behind one of these vessels, which is one of the things that I also mentioned earlier that I really enjoyed watching. Some of the student opportunities are design teams. So two that are most aligned with ocean engineering are the human-powered submarine team and Sailbot. The human-powered submarine team is when you are basically designing submarine to go very, very fast in a straight line. These are generated, you generate power by pedaling something. The submarine is fully flooded. If you were interested in getting like a scuba certification, I think that the team is involved with that. And there's also the Sailbot team that does a lot of work with carbon fiber, or not carbon fiber, fiberglass. HPS also does some stuff with composite building as well. And so those are two good teams that align well with the ocean engineering program. Other things that you could be involved in are different research opportunities. There's a lot of AOE faculty that do research projects that are sponsored by ONR, which is the Office of Naval Research, as well as Navy Labs, the National Science Foundation, and maybe industry partners as well. And so one thing to note here is that your involvement in undergraduate research is a really great gateway if you want to go to grad school. It gives you an opportunity to figure out, am I interested in grad school or not? A bunch of these videos and animations that are shown here are things that my colleagues have been working on in their research programs. The thing with the kind of inclined plate that's splashing into the water is something that I did in my research group. Some students can be paid through research assistantships either over the summer or during the semester. There's also fellowship programs like the National Science Foundation Research Experiences for undergraduate students. Those are very prestigious. You can find more information about the different research opportunities in our department by going to our website, or you could just ask one of the faculty members in AOE. We love to talk about our research programs. A lot of students get summer internships. They can find these through the expo, which is still going on, I guess, this week. Also, the Aerospace Defense and Intelligence Career Fair. In AOE, we also have an alumni mentoring program. And then you can also be involved in the National Security Institute. Some of the professional societies we like are ASNE, SNAME, and then there's ASME, OMAE, which is for offshore structures. There's many scholarship opportunities within each of these programs. If you're an undergraduate student, one thing I want to highlight here is that ASNE has free registration for all undergraduate students for one of their conferences called the MAC. It stands for Multi-Agency Craft Conference. I go to that every now and again. The coolest thing about that conference is that they have live on-water demos of some of the boats. And these are typically like small, fast boats. So you get to go on the boats. I think one year I went on one that was that had an iPad controller, so there were 3 different modes to drive the boat. The first one was a traditional way of driving your boat, and then they said, okay, well then, let's say you're in the James Bond movie and the bad guys are chasing after you. You want to like lie down on the deck, you can switch this into iPad mode and drive your boat with an iPad, or you could have somebody on land controlling and driving the boat with an iPad. So it's pretty cool. The last time I went to this conference, and it's in the summer, I went last year and I rode this boat by Seakeeper, and basically what they had was they have a big gyroscope on the inside, and it's supposed to help with roll stability of your boat. And they could use these on larger ships as well. They have bigger gyroscopes, as well as smaller ones to go on small personal craft. And so we were on this boat, and it was really great. Me with my naval architecture friends, we're like doing loops, donuts in the harbor, and trying to basically hit our own wake so that the boat would go rocking back and forth. Me and my friends were like, yeah, keep going, go faster, right? And there was this poor kid in the back who was an electrical engineering major, and he was like holding on, and he was frightened and stuff, and we were like, go faster. Anyway, it was really cool, and then so the boat would be rocking, and they would hit this button to engage the gyroscope, and the boat would basically just stay still, right? It would just immediately kind of go straight, right itself. We also watched them do this as the waves were hitting the boat, and you could see that the waves were getting damped out as well. So anyway, that conference is free for undergraduate students. If you wanted to attend that, ride the boats, learn a little bit more about boats, design of boats, and research going on with ships. There's a lot of different companies that hire ocean engineering graduates. These are a list of them here. I do want to highlight graduate school options because that's also something that's really, some people don't think about that, especially this week with the Engineering Expo. So students who want to pursue a career in research, either in academia, government labs, or industry, will typically go to grad school. We have our UGG program, which is undergraduate graduate program that adds 1 year to your BS degree, and allows you to double count up to 4 courses in your senior year towards your either MS or PhD program. A typical master's program allows you to get deeper knowledge of your subject area, which in this case would be ocean engineering, and typically adds about 2 years. For a PhD or doctor of philosophy, you become an expert in your field, and this takes an additional 3 to 5 years, depending on whether you do a master's or not. One of the reasons why I decided to pursue a PhD was because I wanted to have control over the projects that I was working on. I didn't want to just every quarter have to design a new component each time. And I thought, I'm an engineer. If I design something right, I designed it the first time. Don't make me do it over and over again. So, the other thing with the master's or a PhD is that you could start your job at a higher salary. There's also a lot of career opportunities in renewable energy, as well as oil and gas, remote sensing. One of the things to note here is that this is a screenshot I took from 2019, where naval and marine engineering was one of the highest sort of desirable majors in terms of how much money you make, what the unemployment rate is, and so on. Okay, so that's all I have. Are there any questions? Okay, thank you. I hope to see you at the MAC conference and we could ride some fun boats together.
Hi, my name's Ella Atkins. I'm the department head of Aerospace and Ocean Engineering, but we're still talking separately because the majors are so different, including day 1 of your sophomore year, where you either take Intro to Aerospace or Intro to Ocean. So right now in Aerospace Engineering, which is what I'm going to talk about now, is one of the most exciting times in history. Yesterday is the first time since 1972 that people were above the altitude that we normally are with ISS. Perhaps tomorrow, for the first time, private astronauts will be spacewalking in a brand new spacesuit from a capsule that has never been used for EVA, extravehicular activity, before. The world, the nation, and the state of Virginia have an unprecedented opportunity to build new aircraft that will be able to carry passengers with electric, sustainable energy from place to place. We have new frontiers in speed for atmospheric flight with hypersonics, with the design of our structures, with building things both on Earth and in space and on other planetary surfaces that we want you to begin exploring by majoring in aerospace engineering here at Virginia Tech. Now, you have to start somewhere. So maybe this is as good a place to start as any. You've all been somewhere by airplane, or most of you have, so you don't really see how it works when you're sitting in the airport. You see this gadget outside the window before you board through a narrow passageway. And you look at it and you say, well, what's going on? Well, maybe there's some magic. Suddenly, this lumbering beast with 100+ people on board manages to get up in the air and seem very nimble as it rolls and pitches and goes from place to place. Well, the whole idea of aerospace engineering is that we're not just teaching you physics and math for the joy of teaching physics and math. We do that. But the reason we do it is so that you can dream and make that dream a reality. Maybe in making things better that exist today, like this tin can with wings you see, where maybe to start out with you think there's a little magic with air and control surfaces, but later you'll learn why these things fly and why we actually have a wing instead of a bunch of propellers to go long distances. And then there's the magic of rocket flight. So here you see the magic smoke that in a circuit can be bad, but in a rocket is very good. you somehow have to create a lot of force, not only to take off from the Earth, but to go so high that there is no more atmosphere, and then potentially to leave the Earth's orbit for another planet or the moon. Our goal is to teach you initially about both aeronautics, which is the science and engineering of flight, how to build the vehicles, how to analyze what they're going to do when you fly them, how to operate them once they actually are ready to go. And astronautics, which teaches you about how things orbit and how they get there, how someone can survive on a spaceship for a long time, and how to use the resources of space to your advantage. I grew up around here in a rural area, and it is the first time in my life that I have had really reliable high-speed internet. Not because finally that fiber came to my neighborhood, but because I have Starlink. Space is not just about exploration and defense. Space is a commodity that we are increasingly realizing. My last PhD student now works at Starlink. He complains occasionally because he'll be out hiking and they'll call him and say, "You got to come back, there's a problem." But it's great. The scalability of that type of system for communication anywhere in the world is huge. In fact, right now, the astronauts on Polaris Dawn are experimenting on Starlink because there are a lot of questions of not only how can Starlink allow everyone on Earth to communicate from anywhere with the kind of speeds we expect at a place like Virginia Tech, but also how do those units work in space? Because as more and more of us, as private citizens as well as government-paid astronauts, manage to make it past the atmosphere into space, we'll need to communicate. And we'll need to do that a lot better than we have in the past. So that's a nice idea, but how do we get there? Well, obviously, you guys are here having some study of math and science in your background, and I might add maybe some computing so that you can actually write and understand code instead of close your eyes and hope it works. In aerospace engineering, one of the fundamental things that we do is design vehicles. And when I say vehicle, it could be something as small as a CubeSat that you hold in your hand, but that catches a ride on a very large and noisy rocket into space. Or something as large as a giant space station that had to be launched in many different pieces and painstakingly assembled and maintained, despite the fact that the people and the robots and the equipment don't have the conventional gravity field, don't have an atmosphere, and everything that is done is dangerous, and there's very little backup. Now, here on Earth with aircraft, backup is the name of the game. You probably know this, but somehow the airplanes, those tin cans with wings that we fly, are the safest form of transportation that we know, despite the fact that you're going almost the speed of sound, higher than you can naturally live breathing the atmosphere outside the aircraft. Day to day, where you expect to wake up the next day and hear that no one died in an airplane that day, despite the fact that there are a few mishaps here and there, like 2 Delta planes hitting each other yesterday in Atlanta. Well, we don't talk about what happens when planes hit each other so much when we're talking about vehicle design, because the idea is that we don't actually want them to hit each other. So that's still part of the work, but what we talk about is what shapes do we choose? We analyze them numerically, so that means math and coding, and then we do really cool experiments. Although Randolph Hall, right outside these doors, is becoming rubble, our wind tunnel is going to be better than ever, and it's going to open in the interim between when Randolph is gone and Mitchell Hall is around. You, if you choose aerospace engineering, will almost certainly have the opportunity to do 1 or more experiments where you look not only at the aerodynamics, the forces and the moments that are applied by air flowing over a vehicle, but also the sound. No one wants a noisy airplane. And when we have the vehicles flying lower, taking us an air taxi instead of ground taxi from point to point, magically skipping over all that traffic in DC as we go from Blacksburg to downtown. We're going to have the chance to make it quiet, to make it efficient, to make it safe, to make the structure cheap to manufacture and reliable so that we don't worry about it breaking up, and to make it controlled in a way that is always safe, even in bad weather and bad winds. We also have new missions. Package delivery. Everybody wants a drone to deliver their package, right? Forget these little trucks. Well, there's a lot of work to make that safe and to make it realistic. You guys would be designing the vehicles, writing the controllers for them, making them work because you understand the principles behind these vehicles and why they're good. So what do you learn? Well, these are cartoons, but instead of learning how a TIE fighter or an X-Wing fighter in Star Wars might operate, which may or may not be very, very realistic, especially in a vacuum of space, you're going to learn how planes fly of all sorts, from tiny, small gadgets to fighters to hypersonic vehicles. You're going to learn how the vehicles that launch things into space produce so much thrust, chemically, technologically, in terms of the structure and the propulsion. When teaching Intro to Aerospace, the first day of class, I always tended to ask, how many of you came here to blow stuff up? Right? A lot of you, right? This is one of the majors where, no kidding, even here at Virginia Tech at the Applied Power and Propulsion Lab, people pay you to blow stuff up. This isn't even a secret, right? So the people who are doing rocket testing have to go off campus a little bit and they blow stuff up. And then there are jet engines being tested every day in this APPL lab. And by the way, they're doing what's called destructive testing. That's blowing stuff up too. So it's so much fun. Now there's a lot of work. You have to know what to do with all the data, because we don't just blow stuff up and say that was a good time and walk away. We blow stuff up, we capture a lot of data, and the idea with that is that we make the systems better. You can contribute to blowing stuff up in a way that makes sense for the rest of your career if you choose aerospace engineering. By the way, blowing stuff up involves low and high speed aerodynamics, dynamics control to point what you're blowing up in the right direction, structures that don't themselves blow up when these explosions occur, of course the chemical propulsion, which is the definition of blowing stuff up, and integrating the whole vehicle together, because when we're propulsing through the air and into space, we want to carry payloads like Starlink, so I get my internet, people who are going to do the first private EVA, and other payloads beyond where we are today. If you join aerospace and you want to join undergraduate research, we have a class for that so you can get credit. And there are a lot of faculty we've hired heavily over the last year or two that are building up their programs and want undergrads as well as grad students to help them out in building their research. This is really useful whether you just want a little bit of experience or whether you're interested in potentially pursuing graduate research at Virginia Tech or elsewhere. We have a ton of design teams. There are 2 facilities that aerospace is involved with. The Ware Lab has teams like the Design, Build, Fly airplane team, and then we have another facility off campus called AEDL, the Aerospace Engineering Design Lab, that has several rocket teams, a CubeSat team, a team that, I cringe to say that, wants to fly an aircraft that you can hold in your hand faster than the speed of sound. Maybe it'll be safe, I hope so, and others. We actually launch a lot of rockets. We have a lot of rocket teams. Some of them, the smaller ones, launch at Kentland Farms, where we also have a paved runway so you can do an unprecedented number of UAS flights, unmanned aircraft systems. We also go to Wallops and other places farther from campus to test our larger rockets and have a lot of collaborations with them as well. All of the majors have this, but AIAA, or aerospace is no exception. We have professional societies. The main one is AIAA, the American Institute of Aeronautics and Astronautics, that has nice conferences every year. Undergrads are welcome at these conferences, even if you're just listening in. A lot of you may need to graduate and move on to careers and contribute to industry ASAP. Others of you may want to stay in grad school. As freshmen, you don't need to decide quite yet, but make sure you think about the options throughout your entire time as an undergrad, whether you choose aerospace, ocean engineering, or something else, right? It is never too soon to say, what do I want? Well, if you want to go into industry right away, fine. Virginia Tech will help you get there, especially if you work hard, do some extracurriculars that are academic as well as just social. But if you want to do something more advanced, the master's degree gives you more deep expertise in a particular subject, so you will get a higher level job when you go into industry or government. And then, of course, if you're really serious about academia and don't want to ever leave, at least for a little while, the PhD can be a direct option. And one of the things that all of you should know is that if you go to a PhD program, your way is paid and you have a salary. You won't make as much as in industry, but you will be able to pursue a deeper education and not ask anyone else to help support you. Lots of careers. I've just been talking about it, whether you're interested in jet engines, designing aircraft of various shapes and sizes, rockets, payloads on rockets, CubeSats, all the way up to bigger satellites, going to other planets, working with robots and the sensors on them. We try to get you the basics in aerospace engineering. What's different about aerospace engineering and ocean engineering from the rest of mechanical engineering and other programs? First of all, 3 dimensions, right? Forget the simple XY heading thing. You have to do all 3 dimensions, X, Y, Z, and you have to rotate in all 3 dimensions. It causes some interesting and exciting math, but it's what has to be done to solve the problems. Also gives you a lot more opportunity to create where you will go and how you will get there. Structures tend to have a very harsh environment. Either the pressure is greater inside than outside, which is the case with airplanes and spacecraft, or the pressure is greater outside than inside, which is the case of deep sea vehicles. So in aerospace, there's a much greater focus on structures that have pressure differential between inside and out. Aerodynamics and hydrodynamics seem to not be linked all that much, but critically, for both air and undersea vehicles, you have to understand the forces and moments and how they give you advantage as you operate, such as having a high lift and a very low drag, much more than if you are on the surface of the Earth. Lots of other questions can be answered about the differences, but if your passion is air, space, or ocean, please choose our department for your major. Next week, just to advertise, get your resumes ready. I know you're already out there this week at Expo. Next week is going to be a specialized aerospace, defense, and intelligence career fair. Some of you may have gone to NSI, the National Security Institute, to check out internship options. This kind of goes along with that, as well as aerospace. There's a lot of companies that allow even freshmen to apply for positions to start early internships and build up credentials in this community. So don't skip this event. It's stage 2, and especially if you're interested in Department of Defense, national security type of activities, I encourage you to attend this career fair next week. Hey, we have an advisor in the audience, and we have 3 total undergrad advisors. Please walk in and see them if you have questions about the degree program in terms of its courses, or whatever in terms of admissions, what are the requirements to choose the majors. And I think that's the end. Quick question? Yep. No, I guess there's a panel, so I can't ask for questions. Yeah, okay.
All right, hi everyone. I hope you're all doing well this evening. My name is Aaron Noble. I'm the Department Head of Mining and Minerals Engineering, and I'm so excited to be here with you tonight. I'm excited for two reasons. The first reason, like you, I was a Virginia Tech student not long ago, and sitting in Burris Hall, I actually got to see Vanilla Ice perform. And so it's a real joy to get to share the stage where Vanilla Ice was, and I'll say he was old when I saw him too. He's very old now. But second thing I'm very excited about is I'm really, really passionate about mining engineering. And like you guys, when I came to Virginia Tech, I knew nothing about it. And I presume that many of you know nothing about mining engineering. You probably didn't even know we offered a program in it, and you have no clue what it entails. That was me. That was me when I was a student. And I sat in a presentation like this, and I'll be honest with you, it changed my life, right? I realized it was a really exciting field, one full of opportunity, and one really full of passionate people. And I set my career that way and have enjoyed it ever since. So I'm going to dive in on this presentation. Like I said, I want to start by looking at a couple misconceptions. Not a lot of people have much information about mining. Many people know nothing about it at all. But what we do know, isn't that the major that's like a dying field? Do we still do mining? Do we do mining in this country? Is that something that's needed? Where will I live? Don't I have to live in like the middle of nowhere, West Virginia, or out in Wyoming? Like, do I have to live out of civilization? And we'll end up looking like these guys in this picture, right? And have almost no career opportunity other than digging around in holes and with a pickaxe. And what I want to do is kind of structure this presentation about systemically addressing these three questions, right? Because I know these are questions you all have. And we'll dive in and see what we find out as we go through. And is mining a dying field? That's the first question I'd pose to you. And I would say, what is society's goals? And it was a real pleasure listening to Dr. Adkins talk right before me, because she talks a lot about aerospace and her department, Ocean Engineering, and I think it represents a lot of what society's trying to do. And I think that's really awesome, and I think you'll find there's a lot of similarities. But if you look here, here's just some cartoons of where I see, what are society's goals through the next 20, 30 years. Obviously, electrification and electrifying the energy system and the vehicle system is a big deal. Looking at renewable and sustainable energy, and also just infrastructure, right? We want to build more buildings. We want to build more roads and bridges. And the common theme in all these is that they require materials. And they require an increasingly sophisticated and complex set of materials, and all these materials have to be mined, right? At some point, they have to come out of the ground. And if you look at it, it's really interesting. We have things like gallium and germanium that are produced in very limited quantities and very sparsely around the world. But as we build more chips and build more solar panels, demand for these things are going to skyrocket, like go up exponentially, and we have to have the mining infrastructure and the mining talent to be able to extract those materials and produce them. And so if you look at things like this, like a modern electric vehicle, it's just kind of littered with these exotic materials and metals. I have another plot I'll show sometimes. If we look at a traditional vehicle, like a Ford F-150, it might have 3 or 4 really exotic metals, and the rest is just iron and aluminum. Something like this would have dozens of exotic metals: lithium, cobalt, nickel, graphite, manganese, like rare earths, all kinds of different materials. And if we look at the demand that's going to be needed to deliver what society wants to do, it's really, really unprecedented. It's unprecedented, the amount of demand of minerals that's going to be coming. I like to depict it this way, which is a little bit more, palatable, right? If we look at something like an iPhone, and you go map that to the periodic table, there's about 75 elements in the iPhone. Each one that has its own supply chain and is mined in a certain part of the US or a certain part of the world, but 75 different types of material have to go into creating an iPhone. Even if you go back 30, 40 years ago, the amount of materials that went into a standard computer chip, you're looking at maybe 6 to 8, and now today we're looking at 70, 80, 100 different types of materials that have to go into a computer chip. I like to show this. I'm pretty complex, you guys all are too. We have about 27 elements in us. So something like an iPhone, this device we carry around, entails a lot more material complexity, right? And so, like I said, if you look at certain materials and certain demands, like things like copper is used a lot in electric wire. I tell my students this without any exaggeration. In the next 2 decades, we will mine more copper than what has been mined in human history. We will do more mining in the next 2 decades than what we have done in all of human history. Think about that. Think about the scale that needs to be, where materials need to be produced, and the talent and the engineers that are going to need to be able to deploy that, and deploy it in ways and in methods that we've not used in the past. So the other question that leads to then is, what do we do, right? Aaron, you've convinced me that mining's not a dying field, that we do need a lot of materials, we need a lot of complex materials. How do we do it, right? Do we still have pickaxes? How is modern mining done? And I like showing this image because this is a picture of one of the modern mines. This is an open pit copper mine in Arizona. This is the Morenci mine in Arizona. I think the second or third largest copper mine in the world. And to give you an idea of scale here, I'm not sure if you can see on the screen, but those big dots you see down on the left side, those are 300-ton haul trucks. They're about the size of a small house. So those trucks are like a moving house. If you want to find an actual like pickup truck on that picture, it's probably like 1 or 2 pixels wide. This is a really, really massive piece of infrastructure, right? The mine itself is a massive piece of infrastructure. That's a surface mine. The other way we can do mining is probably what you think about more common, which is underground mining. You probably think of like crawling around in tunnels. That's not what a modern underground mine looks like. So this is actually the Kimballton mine, which if any of you have been to the Cascades yet, it's about a 30-minute drive from here, 30-minute drive northwest. The Kimballton mine's right next to the Cascades. You wouldn't even know it was there unless you were looking for it. And this is an underground limestone mine where they mine limestone to create chemical lime that's then used as a soil amendment, like it's used for agricultural purposes. So they're mining limestone for agricultural purposes. And there on the left side, you can see you actually drive a school bus into this mine. The ceilings are about as tall as they are here in Burris Hall. So if you're standing in here, this is about the size of one of the openings in the Kimballton mine. This is a really, really large underground limestone mine. What's really cool there in the middle, you can see we took a group of students there, and you can go down 900 feet underground and get really great Wi-Fi service. Maybe not Starlink, maybe not as good as what Dr. Adkins is getting, but you can sit down there and watch Netflix, right? 900 feet underground. And they actually have a shop under there. So they do all their equipment maintenance 900 feet underground. Really cool how much they've built under there. And there on the far right, you can see that's actually one of our faculty members doing underground mapping with drones. And it's a really cool area of inquiry, right? We think about using drones on the surface, and they're used in a lot of industries on the surface where you have access to GPS, right? And drones can use GPS for navigation. Dr. Adkins can talk about that much more intelligently than I can. But what we do underground is we can fly drones in a GPS-denied environment, where they'll do their own localization and navigation simultaneously, and then they can map the interior of the mine. This is really helpful for getting to places that are hard to reach or hard to visually inspect. You can use the drone to get real-time inspection of the mine. So this is pretty cool. You can tell that these are pretty sophisticated and highly engineered endeavors of creating a mine and then operating a mine, right? It's not someone crawling around with a pickaxe, but there's a lot that goes into these. And how do you build the power systems? And how do you coordinate people and machinery and all these different aspects in a way that's efficient, in a way that's safe, in a way that's environmentally responsible? One question I almost always get is, where are the mines in the U.S., right? Aaron, you tell me there's a lot of mining. I don't drive around and see a lot of mines. I'm still not convinced I don't have to live in the middle of nowhere. And so what I did is I went to a federal database, and I pulled up the location of all the active mines in the U.S. And I'm going to show you this map in a second of where all the active mines are in the U.S. And I say this to say these are potential places where you could get jobs as a mining engineer. And I've talked long enough. You've probably got a mental image of what you think that map looks like, and I'm gonna show you what the map looks like now. This is a map of all the active mines in the U.S., and you can see it's just a map of the U.S., right? It's pretty much everywhere. And in fact, many of our graduates, you think they live in the middle of nowhere, but many of our graduates actually live in urban areas, like right outside of major cities. Think Charlotte, Northern Virginia, Richmond. Hampton Roads area. And the reason for that is because anywhere where you have a city, it's like the one thing that's pervasive in the city, and I know there's many people from Nova here, it's like what's pervasive in Nova? Construction, road construction, right? It's like there's always construction going on in big cities, and to support that construction, you have to have quarries and mines that can supply the crushed stone. Just last week, we took a group of freshmen, a group of your classmates, to a mine in Roanoke, where they're actually mining the stone that's going under I-81. So when you go through Roanoke and I-81, they have a big lane. They're widening the lane there. That's mined locally. That's mined right there in Richmond, and we got to see where it was done. So where do mining engineers, what do you actually do, and where do you get involved in the process? And it's cool. If you start to think about it, what's the life cycle of a mine? Right? We first recognize mining is a temporary activity, right? We mine for a set period of time, and then we finish the mining and we go somewhere else. So each mine has a life cycle that starts with number one there, exploration. How do we find where mineral deposits are? And there's a whole branch of mining engineering dedicated to that, right? To where you find mineral deposits and you know, how do you understand the geology? How do you understand what the deposit looks like, how it's structured, what some of the metallurgical characteristics are? That's all on the exploration side. What I've told is that's where all the rich people are at. If you uncover and find a new mineral deposit, you don't need to work anymore, right? You'll be set for life. So a lot of very wealthy people on the exploration side. After that, you get into number two, which is the planning phase. So we can't just go dig a hole in the backyard and expect to start producing copper. We have to be able to plan it in a way that understands the various constraints. Like any engineering problem has constraints, and certainly mining has a lot of constraints. There's technical constraints, economic constraints, legal constraints, social constraints, environmental constraints. And so these begin to narrow down the type of process you can use, the type of equipment you can use, how you're going to stage the mine, how long are you going to mine there. These are things that all go into the development or planning phase. And then kind of 3 and 4 are the actual execution. So there we go, build the mine, and we operate the mine. This gets into operations management. How do you effectively deploy resources? How do you coordinate resources of people, equipment, scheduling, these type of things? And then obviously the back end, when we're done mining, we don't just leave, right? We don't just leave, but we have to return the environment to a way that is better than it was before we started. That's actually the US law. If we go in and mine a place, we have to come back afterwards and ensure that the land is left to a better quality than it was before we started mining. And so there's this whole aspect of mining around the environmental side and around how do we close mines and then, you know, reinvigorate those areas environmentally. And then obviously there's things like sales and actually, you know, pushing product. And then also you think about recycling. And some of the coolest projects I've ever worked on and some of the coolest places I've ever been are actually to recycling plants. Recycling is just another kind of mining, right? It's a different type of material, but we use many of the same processes in recycling that we do in mining. So what do mine engineers do? You get involved with any aspect of that process, right? And depending on what you want to focus on, you'll find a home and you'll really dedicate to the, you know, coordinating the science and technology to do that part of the job safely and efficiently. You also get to work on cool projects and and solve cool problems. So I talked a little bit about the faculty member who flew drones underground, and this was a whole research project and one that's still very active. But I know a lot of our students in their internships and in their full-time jobs do a lot of drone-based surveying, both underground and surface. So a lot you can do around that, and a lot you can do, I think, in the technology space of integrating data analytics, integrating autonomy, remote-controlled equipment. All that's coming to fruition in the mining sector, and this is just a piece of that. The other one, the prior speaker stole a bit of my thunder. We blow stuff up in mining too, right? And we blow up a lot of very large scale blasts. You actually take a whole class your junior year on blasting. It's called explosives engineering, right? So it's pretty cool to take a whole class just on explosives engineering. And we'll see if the video plays. We always have some issue. Next. Oh. There we go. That's an example of a blast you would see in mining engineering, And many of the students will actually go get a job called blast engineer. And they're the ones that actually go design how this blast occurs. And there's a tremendous amount of nuance to this. If you watch the video very closely, the first thing I always point out is you don't just see like one massive explosion, right? But it's staggered, it's timed. And that timing is actually a function of trying to manipulate the waves, the ground waves. Because when you create a blast, you create a shock wave through the earth, and what you don't want to do is have all those waves compound on each other. So what they do is something very similar to like if you wear noise-canceling headphones and you put inverse waves to cancel out positive waves. They do that in blasts, and they'll time the spacing of the individual detonations to try to cancel out those waves. That way people around the mine site, say a neighbor, right, who is a neighbor, you don't want their foundation to crack. You don't want it to destroy their house or anything. So you want to manipulate those waves in a way that doesn't impact that. The quarry we went to last week, they were pretty funny. They said they had a dentist right next door. Like they were about like less than a mile away from a dentist's office. And you can imagine the last thing you want is someone, when they're scraping on your teeth, like the ground to erupt and them to jab you in the mouth with one of those spiky things. So they actually do their blast in such a controlled fashion that even a mile away you get no disturbance, right? The other thing you saw in there in the video is there's actually an objective here. And there's actually several objectives, which is pretty cool. One in this one, they were trying to move that material into the hole right next to it. So you probably saw as it was blowing up, the material was actually being pushed over. And there's a specific way you can design the blast to create that pushing action. The other thing you want to do is you want to shatter the rock, right? That's what we do in mining engineering, make big rocks into small rocks. So you start with one gigantic rock, which is that entire slab, and then you want to break it down into finer rocks that then can be handled and manipulated and processed. What you don't want to do, though, is create rocks that are too fine, because that creates other issues like dust and environmental issues. So there's this really sweet spot of like, how do I move the material? How do I manipulate the waves to not impact my neighbors? How do I shatter the rocks enough but not too much? And that's why people make a living as a blast engineer, because they know how to figure all those things out and then adjust it to the local geology. Really cool field, and I think a really cool application of engineering principles. But in talking about what mining engineers do, I think it's important to ask the question to you guys: what problems interest you? And if I were a student again and thinking about what I wanted to major in or what I wanted to do for a career, I would probably start with this question. And I would say, what are the problems that really, really interest me? That would be the first question. I would probably then ask, who are the type of people I really want to work with to solve those problems? And then 3, I would choose a major that leverages both of those to the greatest extent. But we'll start with problems. So what kind of problems interest you? And as you're thinking about that, I'll show you some of the problems that we address in mining engineering. So things like management. Big component of running a mine is managing people and resources, right? A big component is design. How do we actually design the structure within the mine to be supportive? I talked about an environmental side, but there's also these other cool things like finance, right? And I'll talk more about this in a second, but finance is a big area of mining. A lot of our students do have a very financial focus. They want to do something in the finance sector. Mining is a really good way to do that, and being an engineer gives you a lot of leverage there. But I show this because I also want to come back and put faces on many of these. And these faces are friends of mine, right? These are friends and colleagues of mine and people who graduated from our department. And so calling out to some of them, like Carrie Cossey, class of 2000, she's actually a president of a company called Ball. And you may never heard of Ball, but if you pick up a can, like a Coke can, there's a 50% chance it's a Coke can, right? So out of all the cans in the world, about half of the market share is owned by Ball. This is the biggest canning company in the world. And she's a regional vice president, sells all the cans in the Middle East and Europe. Like, really cool position. She started in the aluminum mining industry and then worked her way down the supply chain and now manages hundreds of people all over the world. Another one really cool, Richard Bishop, he's a faculty in our department. He's a professor of practice. He's the one who does the drone flying. And in a former life, he was actually a banker. He was an analyst with the Royal Bank of Canada. And you're like, why would a mining engineer work for a bank? Well, mining projects are really big, really, really big investments. Modern mine, we're talking about probably $1 billion to start a new mine with a B, $1 billion. So you obviously have to get a lot of input from banks and from different financing agencies. And those banks hire technical people to evaluate the mine plans, right? So he was an analyst at the Royal Bank who evaluated mine plans, and that way when people would come and say, we need $1 billion, he could look at it and say whether it was a good plan or not. And there's a couple other. We've got one student, Tyler, my good friend Tyler Faulkner, who now is a software specialist. He works on and develops software to support the mining industry. And then San Akanyami, who just graduated a couple years ago and now does a lot of permitting for Tesla and permits a lot of Tesla's facilities all over the U.S. So what about Virginia Tech, right? And I like to say at this point of the presentation, I think you guys have already made the best decision you'll ever make in your life, and that's to be here at Virginia Tech and to be a Virginia Tech Hokie, right? You can't go wrong after this. You're all going to have incredibly successful careers. If you do choose to come into mining, here are some of the distinctives of our program. First of all, mining is not a very large field, and Virginia Tech is an extremely well-renowned program. So by many metrics, we don't get ranked like some of the departments do, but by just about any metric on student outcomes, on research outcomes, we're number one, and number one significantly. And the data shows about a quarter of all the mining graduates in this country have come from Virginia Tech. So a lot of people in high leadership positions, they also got to sit in Burris Hall and listen to Vanilla Ice at some point in their past. We also, one thing I really like about our department, Virginia Tech is massive. Everything's done at tremendous scale, right? We have over 10,000 engineering students now. Mining engineering helps make this gigantic university very, very small. So we have fairly small classes, maybe 30 to 40 students. And in 2021, the university recognized us as an exemplary department, like the best department for student engagement. We do a lot with our students to help you be successful and to help you have an amazing career. We also, I think it's a misconception, mining is actually very diverse. I looked at our class of 2027, and about 30% is female, which I think is in line or better than most other departments in the college. Some other things about our curriculum, we really focus on the skills that you're going to need to be successful. And I'll highlight bullet 2 here because this is a class I teach. I teach a sophomore course that's a specialized leadership training course. So it's about how do you understand yourself and how do you understand yourself as a leader, and then how do you carry that out into developing responsible mining projects. It's a really fun class. We take an overnight field trip to a corporate level, like a C-suite leadership training course in Richmond, and we get to do a lot of really fun activities there. Another one kind of highlighting leadership development, that picture on the bottom left, that's a group of students we took about 3 or 4 years ago. They got to take a private jet to Peoria, Illinois to Caterpillar's headquarters, and they got to do a leadership training course with Caterpillar, and they got to fly on a private jet, which was pretty cool. We have another group of students there right now. They're doing the same leadership development course this week. They didn't take the private jet this year, so shame on me. And then we also, like the prior department, we do have a mining-specific career fair. Our career fair will be coming up in about 3 weeks from now. So if you are interested, you are able to come to our career fair. And every year we do have first-year students that get internships at our career fair, sometimes mini internships at our career fair. And the reason for that is because there's just tremendous demand for Virginia Tech mining engineering graduates. Going back decades, we've had 100% job and internship placement. I can say last year, 70% of the undergraduate students got multiple offers on internships, and probably more than 70% got multiple offers on full-time jobs. There is tremendous demand, and we have a pretty robust scholarship program. I like to show this graphically because this is what actual numbers were last year. If you look at like a typical class in mining engineering, maybe 30 or 40 students. I think our junior class right now is in the 30s. Senior class is actually a bit smaller, around 20. And in a couple weeks, we'll have almost 60 companies coming to our career fair. So 60 companies coming to hire 20 graduating seniors. You can see where you get leverage in this discipline, hopefully. And the jobs are pretty good. So we got recognized in CBS News a couple years ago for some of the highest paid college majors across any discipline, not just engineering, but any field. Mining engineering was number 8, and our very close sister discipline in metallurgical was number 6. You guys have all seen Holden Hall. Holden Hall is the home of mining engineering, and we have some really fantastic facilities there. So world-class labs. We have in the bottom left, you see our Center for Autonomous Mining Systems. That's that big sandbox you see when you walk in the tunnel going to Lavery Hall. And throughout the semester, I know mining is a bit strange. We're one that you've not heard of. You probably have more questions than I'll be able to answer today. So we've scheduled a couple events throughout the semester. If you want to learn more about mining, you want to get into a more intimate environment with our students, with myself, with the other faculty, these are some options. So this Friday, we'll be having an open house in our Center for Autonomous Mining Systems. I believe it's around midday. We've got some flyers outside if you're interested in that. We can get you the time and location. We'll have food, we'll have drones, we'll have students and faculty. It'll be a good time. Here in the first week of October, we'll be taking another Blast Day field trip. So if you want to go see this firsthand and have the opportunity to detonate, you can sign up and we will take you on the Blast Day trip. Or if you just want a free lunch and you want to have a lunch with me or you want to have a lunch with one of our current students, get in touch because we host those all fall and we'll be very happy to host you at our lunch. If any of those sound interesting to you, you can use this QR code on the screen to sign up. This will get you in touch with our academic advisor, Michelle Crotto. She'll be in the back of the room as well after the event is over. And you can also get in touch with her through that form. You can get in touch with me. And we look forward to seeing you. My name's Aaron Noble. It's been an absolute pleasure. Thank you.
Welcome, everyone. This is the last one, just so you know. All right, so I am Dr. Natalie Chewbacca. I'm a faculty member in Industrial and Systems Engineering, and pretty soon Dr. Van Aken's going to come up here as well. We're tag teaming this. And just so you know, ISEs typically don't blow things up. Just want you to know that right now. But we do other things, so hopefully we'll let you know about that. What is ISE? What is Industrial and Systems Engineering? This is not a typical question that people can answer very well, and I'm assuming that most of you can't, so that's what this is about. All right, so what is it? This is a formal definition, and we're going to kind of work through it as we go here. So what is ISE? The design and improvement. So you'll see that pretty much throughout all these engineering disciplines. We're designing things, we're improving things. But specifically for us, it's for complex work systems. So complex work system, up there you see, it involves people, information, materials, equipment, energy, sometimes other things. Those are just examples. So one of the nice parts about ISE is that we cross many fields. So you've heard lots of application areas today, right, with space, with ocean, with mining, and with ISE, you can kind of go into any field that interests you, all right? Because we look at it from how do we integrate these elements together, and so that's one of the big selling points of ISE is just the many fields in which you can go into. All right, so I'm gonna give you an example. Thank you, Dr. Noble, for setting me up with this. And so if you think about the phone here, and we should plan this better, but you know, it just worked out here. So what do different engineers do on the phone? All right, you know now about mining engineers, how they might contribute to the iPhone. And if you look at the other pieces, right, a computer engineer is going to design the chip, maybe the storage. You've got mechanical engineers going to complete those CAD drawings. You might have optical engineers, material science in there. And so what do ISEs do? Where do ISEs fit in that? And so I'm going to kind of talk about this as we go through the different parts about ISE. So that's the big question. Where do we fit in? So one thing to think about is we're the integrators. So if you go back to that idea of a work system, these people, I'm going to go back here, right? You can design a phone. We've got one phone. It's awesome. You design this, and it works. But how do we get that out? How do we produce, you know, just the number of phones that are even in this room? All right, so ISEs will look at that full supply chain. We look at everything that happens in the facility. We make sure that those phones that we're producing, how many we need, they're to the correct quality, and we get out as many as we need across, you know, around the world. So that's sort of where we look, where we fit. We can think of it as the integrators, and I'll go into a little bit more detail on this. So there's 4 main areas in our program, and manufacturing, operations research, human factors, and management is how they're labeled. But I'm going to tell you a little bit more about those, and you'll hear some kind of keywords and things that might be of interest to you that fit into these different areas. All right, so the first one is manufacturing systems. And this is the historical application of ISE, but we are significantly more than that now. So what manufacturing systems do is we design and improve. You recognize that from the definition at the beginning, right? We're designing and improving, in this case, manufacturing facilities and operations. And so if you think about that iPhone, the production of that iPhone, what's happening in that facility, how are we moving the materials around, how do we arrange, which machines do we need, how do we arrange them, what's the production planning for them. So we've got the mining engineers that are bringing us these raw materials, but the supply chain to manage those is done by ISEs, all right? And then how much do we produce through the facility? Do we have the labor that we need? Those sort of questions. And we address this typically from a mathematical perspective. So the business folks think about it from a business perspective. We look at it like a giant story problem. It's kind of the best way to describe it. All right, so here's some just images of that sort of facility. So if you look at the one in the middle, right, the robot that's laying the phones in those fixtures, so that's something a decision that an ISE might make. So you look at it and go, okay, how are we going to move these phones throughout our manufacturing facility? We need them to be oriented in a specific direction. We need them to proceed at a certain rate. What sort of equipment would make that happen? All right. The next area then is operations research. And this is the most heavily mathematical side of things. So here it's the application of advanced mathematical methods and simply to improve decisions. So those decisions could be in any sort of situation. Lots of supply chain examples. This is where machine learning and data analytics come into play. And those models might be predictive. As an example, in a manufacturing environment, something that's kind of new is using machine learning to predict when certain things might happen. So when might a machine break down? We'll use lots of data that we'll gather, make that prediction. That way we can prevent it. We can do some maintenance ahead of time and prevent that breakdown. The examples you see up there, vehicle routing, the UPS, FedEx delivery trucks. There's a UPS hub right here in Roanoke. So that packages come into that hub, and there's hundreds of trucks every day. How do we decide which packages go on which truck? What route should that truck take on that particular day? And that's one problem that ISEs might solve using operations research, mathematical modeling. All right, so some images about that. So you see on the right, these lines going across the whole world. The supply chain, hopefully lots of you are aware of what the supply chain means, right? You've all experienced potential breakdowns in the supply chain. This is something that ISEs address from a mathematical perspective. We look at how much inventory do we need, where, why, when, what shape, and how do we make that happen? All right, management systems, so this is the third area, and this is dealing with the design and improvement, again, of systems used to manage business enterprises. So Aaron talked a little bit about operations management within mining. We do that as well, so we look at the system, a business system, and say, okay, strategic planning. So if we've got a strategic plan, how is that going to affect the rest of our business? How is that going to affect the outcomes? And again, we look at it from a mathematical perspective and systematically. So within this, systems engineering falls under this, which is kind of another subfield, I would say. And with systems engineering, we're looking at the entire life cycle of something. So it could be an aerospace design, it could be an ocean, a shipbuilding, it could be a mining operation, but we're looking at the entire system. Are we meeting the requirements? Are the pieces fitting together? How do the pieces affect each other? Such that we're getting what we need at the end. And again, looking at it mathematically, integrated throughout all that. All right, the last area then is our human factors and ergonomics. And this, again, we're designing and improving. In this case, we're looking at products and systems, anything that humans interact with. And here we're looking at the interaction both cognitively and physically. And so things such as user design, user interface, those come into play here. So some examples on this next page, right? Your iPhone design, so this is Another aspect where ISCs might fit in is how are people interacting, how are people using this particular device. And then also on the ergonomic side, say within a manufacturing facility, you see the little cartoon there on the bottom right of the person working, and we're designing that workstation to enable the worker so things are at the right height, the right place, the right time, such that the worker is efficient. All right. So there's the 4 areas again that make up ISC, and when you focus on this, one of the unique things about our program is that you'll take classes in all of these areas, and then you have some room to take some electives, and Dr. Van Aken will tell you more about that. So back to this first slide, or the first definition. ISCs design and improve complex work systems, and that involves people, materials, information, equipment, and energy, and really, honestly, other things. So, you know, I would say if you're interested in all kinds of any sort of application area, maybe you're not even sure what you're interested in, ISC can be a good route. We work in many different areas, and lots of our students, there's a list here of different types of things our students do and jobs they go into. So it's super flexible, and we get to engage with lots of different people in lots of different areas and sectors. So with that, I'm going to turn it over to Dr. Van Aken, and she's going to tell you a little bit about ISC here at Virginia Tech.
All right, hi everybody. I'm Eileen Van Aken, Department Head for the Grado Department of Industrial Systems Engineering. I'm also a triple Hokie. I've been on the faculty for quite some time and have the honor of leading our department. We have a wonderful team of faculty and staff and many, many students. But I got all my degrees here as well. So I distinctly remember learning about industrial engineering. We were called Industrial Engineering and Operations Research at that time in this exact kind of session. It was not in Burris Hall. I don't remember what building it was in. And that's when I learned about it. I did not know about it before I came to Virginia Tech. And then I just fell in love with this discipline and haven't looked back since then. I just wanted to kind of add on to what Dr. Chewbacca said about the ways that we're concerned with work systems, and we kind of used the example of a cell phone, threaded through the different sub areas that ISE encompasses. A couple other examples you could also think of is a car. Lots of other engineers would be involved with designing the mechanical system, the electrical system, but we'd be responsible for figuring out how to manufacture it in a safe way at an economical price that can get to the customer and meet their requirements. So again, having the right stuff, the right tools, right equipment, right people, right number of people at the right place at the right time, so it's all optimized. And so that's what we love to do, is to look at things to see how they can fit better together with a really strong emphasis on technology and equipment. So we geek out on that as much as any other engineer, but we also really love to integrate, how do people integrate with that system so that we can make sure that we're optimizing a system also from this perspective of humans who are part of the workplace and humans who are customers of the products and services that our discipline creates. The other thing that's kind of interesting to think about is, if you think about how long does it take you, for those, if you're on the bus, or maybe you have a car and you're driving to campus, does it always take exactly the same amount of time to get to campus? Maybe it ranges between 3.5 minutes and 8.2 minutes, depending on the traffic lights, depending on traffic, the time of day, whether you're trying to go around the drill field during class change time. So there's inherent variability in everything in the world. And so as ISEs, when we think about how long it takes a production worker to run their process on a piece of machinery, it's always not going to be deterministic and exactly the same, because there might be a defect in the material, maybe they're a new worker, they haven't been as trained as much yet. So we also take a lot of probability and statistics to be able to learn how to deal with that uncertainty and that variability when we're making all of this stuff fit together as best we can. So I just wanted to, the theme is that, we're the discipline that really looks at how can we create products and services, because there's many disciplines, many applications in the service sector that we work on, how to create those products and services at a high quality in an economic way, because who's going to buy something that costs $20,000 when an iPhone might be, what is it now, about $1,000 or something like that, $1,200. So if somebody designed a $20,000 cell phone, they're not going to be interested, at least maybe not today. So we get very much concerned with economics and money aspects of how we can have businesses also be, be profitable if they're for profit, or financially viable if they're not for profit. All right, so that's a lot about what is industrial and systems engineering. We also wanted to tell you a little bit more about what is unique and we think special about ISE at Virginia Tech. So some of you already know you might want to come into ISE, and maybe that's why you chose Virginia Tech. Some of you might be undecided and you're trying to think about how to decide amongst the different engineering majors. And I would just like to add my point to what Dr. Noble said. You've already made the best decision. You've chosen Virginia Tech engineering, and really you can't go wrong in any of the engineering. We have such strong engineering programs here. But we did want to tell you a little bit more about what's maybe unique and differentiating things that can help you think about a little bit more, to know a little bit more about our department. We're very proud that we are very highly ranked, and of course there's some disciplines where they're smaller and they don't have formal rankings. We are ranked by US News and World Report. When I came as a freshman and learned about ISE, or IEOR at the time, we were also ranked in the top 10. So we've been highly ranked among all the 120 IE programs in the country in the top 10 for over 40 to 50 years. We were among the first industrial engineering departments in the country, and we started in 1920 as the name commercial engineering, as a fun fact. And so, that's definitely something that we're really proud of. But if you know about how these rankings are, they're very subjectively determined by leaders like me, department heads in the field. But I would offer to you that there's a lot of objective data where we're very proud of our students that show how strong our program is. And two quick examples. We send every year our senior design capstone, 1 or 2 teams out of 40, to our national conference, the IISE conference. And that capstone competition has only been in existence, I think, for 4 years. Dr. Chewbacca and I were talking about this the other day. Virginia Tech team has won first place, second place, fourth place, and first place out of 20 national finalists out of hundreds of applications that went in. And the highest honor given to an undergrad student by our profession 3 times in the last 5 years has been won by a Virginia Tech ISE student. So that's just to kind of add some additional perspective and evidence, if you will, about why the program is strong, highly viewed, and very well respected across the country, and by employers that really actively seek to come to us in order to hire our students. And then along those lines, the vast majority of our students do internship or co-op, many of them multiple summers or semesters. Here are some examples of a number of the companies that hire our students in internships. These are ones that you can see, of course, are manufacturing companies, but some are consulting. There's healthcare. There's Walt Disney World, entertainment. They hire a lot of industrial engineers. UPS, FedEx, they have a lot of industrial engineers in their business. We had a lot of students this summer working at Boeing, not just their manufacturing facility in Charleston, South Carolina, but in other parts of the country as well, working in manufacturing as a manufacturing engineer, or working in systems engineering, for example. So these companies that I've listed here also happen to be many of the same ones, not necessarily all, that also sponsor our senior design capstone project, which is a 2-semester capstone where all of the projects work on a real problem with a real client. And so these are a lot of some of those same companies, but sometimes there are also some smaller businesses, some not-for-profits. We've done projects for local and small business, but also for very big projects as well. In terms of internships, what's another thing that's unique that we would want you to be aware of is that we have some very generous alumni that have not only given us endowed scholarships, and I'll mention more about that in a minute, but we also have alumni that have given us money over like a 5-year commitment, such that we give out scholarships just within our department for internships. So when you're living in Blacksburg and you can't sublease your apartment because it's not like there's a huge influx of people all the time in the summer here, but then you want to do an internship in Seattle or Phoenix or Charlotte or Washington, D.C., and that's not where your family is and you can't live at home, we use these scholarships to help offset the living expenses so that somebody can pick the internship that they really want, rather than picking one that maybe not as much what they want, but because the lower cost of living. So that's something that we're really growing more and more. We have $35,000 a year that we give out to students for internships, and it is need-based. So that's one thing that we also wanted to mention. 42% of our students belong to one of the organizations in our department that are student organizations. As many of you know, there are so many student organizations all around campus, and our students do that as well. But these are the names of some of the ones that we have student chapters of. And so our main overall professional society is IISE. That's the annual conference every year. It was in Montreal last May. It'll be in Atlanta next year. We always send about 10, 15, maybe 20 students where they don't have to pay anything, just about anything. And so we're really proud to be able to have our undergraduate students, and that's undergraduate students. We have a lot of graduate students that also attend that annual conference. So there's a lot of opportunities to really gain some experience in like volunteer leadership and service during the time at Virginia Tech and in these departments. And many of these student organizations have received national recognition. Alpha Pi Mu is our honor society. Out of the last 17 years, we have won first place in the national chapter competition 16 times. When I was a student, I was president of Alpha Pi Mu, and I felt a great deal of pressure to continue the tradition of how the chapter did each year. And so we're really proud of those organizations. They really do a lot for all of our students. Many of our students complete a minor. There are a lot of minors around campus. These are the ones that are very common in ISE. We have a unique arrangement with the Pamplin College of Business so that the courses that you might take that might be an ISE technical elective are really double counting as the course that the College of Business would count, maybe a cost accounting class, but we have an industrial cost control class, so that subs out. So you really can get that minor with far less extra courses than you would if you were in any other major. But there's a lot of other minors that our students do as well. Quite a lot of students participate in undergraduate research. This is something that is really kind of characteristic of the College of Engineering. We have a very strong focus on experiential learning. In addition to internships and co-ops and service learning and things like that, participating in undergraduate research is another really critical way to do this. And I would say whatever major you go into, and even if you don't think you have interest in graduate school, and if you do have interest in grad school, you definitely should consider doing undergrad research in whatever department you go to. But even if you don't know you want to go to grad school, there's so many benefits to working on undergrad research because you can work in a smaller group or even one-on-one with a professor, be in their lab with their grad students. You can learn more really leading edge topics that align with their research before that knowledge has percolated down into required or elective courses. So these are just some pictures and examples of students that have worked in areas where they're looking at slips and falls and kind of biomechanics so that we can have occupational settings like a UPS driver carrying packages or people in a manufacturing facility or somebody in a Lowe's distribution center so that they can be safe and avoid slips and falls, because that's a really huge problem in many industries and back injuries from that. And then there's people working on heads-up displays, human-robot interaction. So those are just some examples. I've personally advised a lot of undergrad research teams over the years on how to implement lean manufacturing or lean production principles in hospital operations. And so we've worked on how to reduce non-value-added activities, improve the patient experience, make the job easier and less demanding for nurses and doctors, in the ER, in the OR. And so it's not just in the physical labs. We have two. There's undergrad research opportunities where you can work with faculty that don't necessarily have a physical lab, but their lab is really outside in industry, and you can be working on things like that as well. More than 20% of our students have some kind of international experience. We really have been working to grow the number of our students that get exposed to, a short term, like a 1 week or 2 week experience during winter break, or a summer experience, 6 weeks, or even a full study abroad during the semester. So we have quite flexibility in our courses where we offer some of them as trailer sections, so not just one semester only, and we offer many courses in the summer. So it is still possible to take advantage of some of these international opportunities and still be able to graduate on time. I had a student that went to, I wasn't her advisor, but I kind of mentored her when she was going to Brazil, where we have a student exchange program with a university in Curitiba, which is in the state of Paraná, and she was able to do spring semester there, which is their winter, and come back in time to make up summer classes, and she graduated in 4 years and took the courses in Portuguese and had not learned it until she went to Brazil in an immersive language class for about 4 weeks before the semester started. So that certainly is possible. And we do offer some scholarships just for study abroad, just from our department. And in terms of scholarships, we have over $240,000 that we gave out just last year to ISE students. Compared to the size of our department with about 550 students, that's actually a very high amount of dollars per capita, so to speak. And so we just have very loyal and very generous alumni that often go into very high leadership positions, and then they're in a position to be able to give back to the department and to Virginia Tech to help us create more opportunities for students. Our students average about $80,000 as a median starting salary. That's about in the middle or so of most of our engineering departments here at Virginia Tech. One of the things that is maybe also interesting to understand about the future of this discipline is it might be a little hard to read on the screen here, but the Bureau of Labor Statistics does an outlook for all kinds of disciplines, and they actually predict a 12% growth in jobs for industrial and systems engineers over the next 10 years. The first time I started tracking that data, the growth was going to be 6%, then it was 8%, then it was 10%, and now it's 12%. And so you can think about a lot of the really complex problems that the world has, and how do we operate and trade and buy stuff and interact with products and services. You can see that there'd be a really great need for a lot of industrial and systems engineers working in concert with many other engineers in all of those kinds of organizations. That 12% outlook, at least as I understood it at the time that data was published, was the highest out of any of the engineering disciplines. So that's you can be assured that you would be able to have pretty good job security in terms of being able to find jobs, not only because you can work anywhere, but also because of the need for more and more ISEs in the future. One more data point that we became aware of recently is, there's always these, Dr. Noble shared one for mining engineering, and he and I were emailing about that, like, hey, look at that, that's really cool. Like, it's great to help students understand more about where are some of the, not only the prospects to, earn a good salary, but also to do impactful work. But of course, salary is important. And if you look at this study by pay scale, they just had the highest paying college majors in the US, not just engineering, but highest paid majors after 10 years and after 5 years. And the ones that are highlighted all have to do with industrial and systems engineering. Operations research is a fundamental part of what we do. We used to be even the name of our department. One more that actually is up here we didn't circle is one my faculty reminded me has a strong connection to human factors and ergonomics is interaction design. With all the work we do on user experience, user interaction, and so that definitely highlights the important, the prospects and the opportunities you would have. The last thing I want to share is we have a very good placement rate. We don't have quite the same number of 2 to 3 times the number of our graduating seniors coming for our career fair as in mining engineering. That's very impressive. We're going to have to compare notes with you, Aaron, to find out how you pull that off. But of course, our students use Expo, their internships, their capstone projects to pursue jobs. So 95% of them either have a job at the time of graduation or are going to grad school. And we do have an accelerated undergrad program. That is something that we are strongly encouraging students to think about early on, and where you get to double count some courses, as our first speaker mentioned. So we all have that, and so that is something you should just be aware of. So rather than maybe getting like 3 minors, maybe think about doing the accelerated undergrad grad program where you can get a master's just 1 year after your bachelor's, with about the same number of credits, if not less, than 3 minors might give you. I'm not saying don't pursue minors, but just kind of maybe keep that in the back of your mind as you go through the coming years. So the breadth of the job opportunities really makes this is kind of, a lot of people use a term that this is a discipline that's pretty recession proof. It doesn't have the kind of like cycles in hiring like some sectors have, because you can work at Disney World, Capital One, in a hospital system. So you can imagine that there's just that many more job opportunities that make it very flexible if you really like to pursue different kind of things. The last thing I want to say is that we also are very proud of the way that we work with students and our course offerings and our great advisors. And we have our last year's data, the newest data that we got was our 4-year graduation rate was 78%. The college average, Tasha and Marlene, is 55%. Is that about right? So that's significantly higher. We'll probably see it go down a little bit, just given some of the struggles and a lot of students have had, and catching up and math readiness because of the pandemic. So we're all working really hard across the entire college on how to help students be prepared for that. So ours might go down a bit, but will probably still be higher than the college. So that's really important, understanding student debt. So we take really seriously the time and the money that you invest with us so that you can learn what you need to and then go out and do good work and make us proud. So the last one more thing is we also have 2 professional master's programs. So we have many students that have other engineering degrees that get their master's with us while they work full time. We have one in systems engineering and we have one in engineering management called the Masters of Engineering Administration, or MEA. So tuck that away in your mind. If you don't choose ISE, that might be something that you might want to pursue as you advance in your company and to want to develop more expertise, and maybe have your employer pay for it while you work full time and go to school part time. That is all that I have to share. Thank you so much for your attention.
Okay, so what I would like to do is to invite our panelists to come on stage. We will have a seat up front, aerospace and ocean engineering, and then we'll have mining in the middle, and then we will have the other program on the end. All right, and so for those of you who have not been on stage, feel free to introduce yourselves as well. And so we'll start with our first table here with aerospace and ocean engineering. And can you tell us a little bit about why should a student choose your major? Is it on?
Okay. Oh, okay, win. Awesome. So, what's up, y'all? My name is Nate. I'm a senior in aerospace engineering here. I am in the UGG program, which means I'm also starting my master's. So, starting that in aerospace as well. I'm going through my senior year, and I'm going to complete the rest of that part-time once I start. So, if you have questions about that later, I can also go through that. Do you want me to do my introduction? They do introduction?
No, you can do your introduction and then we will answer the question.
Okay. So the question was, why should a student consider your major? I could talk about aerospace engineering for days, and I think Dr. Atkins definitely hit on a lot of the key points as to why to choose either aerospace or ocean engineering. Both of them have a lot of excellent job opportunities, and I think both of them are heading into definitely golden eras of both of their respective disciplines. I mean, aeronautics is heading into sustainable aviation, is heading into larger efficiency gains in commercial aircraft. We're getting into a whole bunch of new different technologies in electric aircraft. Space is heading into obviously a golden era, as it has been for the last decade. Definitely a lot of exciting things, a lot of new rocket innovations and a lot of new satellite innovations that are coming around. I know definitely a lot of people were talking about this when James Webb was launched. A lot of aerospace engineering graduates from Virginia Tech got to work on programs like that. So if things like that are the things that excite you, that drive your engineering passion, that got you to Virginia Tech in the first place, definitely consider aerospace or ocean engineering as a major.
so I'll talk a little bit about ocean engineering, which I already talked about earlier, but just why you should consider ocean engineering is there's a lot of job opportunities. I think that the work is actually very diverse and very interdisciplinary, so you could work on a lot of different things. There's a lot of job opportunities, especially with the Navy. And then if you heard in the news about the Titan imploding, there's also things that you can do for commercial type of applications as well. The ocean is not as well explored as some places in space, so it would be really great to be able to really map underseas as well, and really understand more about the planet that we live on. The Earth's surface is 71% covered in ocean, so that's another reason to consider ocean engineering. There's a lot of really cool autonomous boats, which I've also talked about a little bit earlier.
Hey everyone, I'm Brian Arnold. I'm a senior in mining engineering. I'm also just starting my accelerated master's program, so the UGG program, but for mining engineering. And the question is, why should a student consider your major? Well, Dr. Noble's done a great job of kind of highlighting the major points there. I can talk all night about scholarships, internships, job placement, job demand, and pay out of college. But really, when it comes down to a class basis for the major things we're doing here at Virginia Tech, mining provides a really niche and specialized focus. So if that's something you're looking for, mining will bring your focus and hone it. In terms of class size, definitely a smaller class environment. So you get to really mingle with your classmates, create some connections, and your professors know your name when you go into class. That's one of the highlights for me. When I go in and I learn, it's not just like sitting in the back of class in a lecture hall. I get to be in the front, they ask me questions, we have conversations after class. So it's a really productive learning environment. Yeah, and again, the statistics don't lie between job placement, salary, things like that, but really get to grow with your classmates. They support you through your entire journey, and the professors truly do care. For the explosives class that Dr. Noble was talking about, it's a really fun class, but the homework one time was stumping me, so I went to office hours, and I talked to the professor, and I was like, what's going on with these problems? Why do we do so many of these? Because those classes really play into real-world problems. The homework you're doing for that class is what you'll be doing in real life, and there's real implications there. Safety is a big part of what mining engineers do, and so through those classes we learn how to improve safety, implement best practices, and really make the world a better place, head towards better change.
Yeah, thanks, Brian. I'm Aaron Noble, Department Head, Mining and Minerals Engineering. Brian hit on a couple points, and I'll embellish a couple of them. Pretty fun. You know, we do have fairly small classes, and I make a point to learn all my students' names on the first day of class, and really try to build relationship with the students, because I know that you guys are going to be the leaders, and I want to be a part of that, and it's really an honor to be a part of that. And I recall one year we had a student, it was on the day of final exams, and we had one of those 7:45 a.m. final exams, and a student didn't show up, so I actually got on the phone and called the guy. I called him and I was like, hey man, you're gonna miss the final if you don't show up, and he came in later, finished his final, and did well in the class. But that's the kind of relationship I like to build with the students, where, you know, we're all in this together, and we're gonna solve problems and work on cool projects. And I think, why would you consider mining engineering? One is that camaraderie that's pervasive throughout the entire industry. But also, we get to work on, I think, really meaningful and really impactful projects. What I showed on the slide today, you know, there's no small mining operations, right? They're big, they're huge feats of, you know, human endeavor, and we get to be a part of that and really have a material impact on that. And I think that's pretty cool. So, thank you.
My name is Bella Princey, and I'm a senior in Industrial and Systems Engineering. The question is, why should a student consider your major? I think it is really important to know what you can do with your major post-grad. So the job opportunities within ISE, what's really cool about that is you can work within any industry. In some of my internship experiences, I've worked in aerospace, technology, doing kind of software work, but to me, my favorite thing about my major and what is unique about ISE is the people as well as the classes. So we have a very strong alumni connection. In some of my past internships, I've been recruited by and worked with different ISC alumni, which is just really strong connection to have to those people and to get to work with them. And I really think what stands out to me a lot about ISC, Industrial Systems Engineering, is the variety in our classes. There are 4 main categories, as Dr. Van Anken was talking about: manufacturing, operations research, management systems, and human factors, yes. So you really get to touch upon all of those 4 areas while you are taking your classes, and each semester you're kind of touching upon what those 4 different areas are, which I think leads to a fun, kind of diverse schedule in what you're doing in your classes. You could be working on a project where you're doing applied mathematics, taking what you've learned in linear algebra later in your sophomore year, and then putting that into a math project in your deterministic operations research class. And then you could be developing an idea for an app in your human factors class. So there's just such a variety in what you get to learn within your classes, which is what really stands out to me being a student and what you're going to study. You're going to be working on those classes for the next 4 years, having something that you look forward to studying in class, going to class every day. And then also the people, since we are kind of like a medium-sized major, you get a really tight-knit community within ISC. I've really found my place here, and I've made some of my best friends through this department. And there's so many professional societies that you can mingle with your peers in and out of class. It's just a great community, and I'm sure there's that in all of the engineering majors, but it really stands out to me in industrial and systems engineering. Yeah.
I'm good.
Okay. All right, we'll move on to the next question, and we'll start with the middle in mining engineering. Is that okay? And we will ask the question is, what was the neatest aspect of your undergrad experience that you have taken advantage of?
For me, this is probably undergraduate research. I've been an undergraduate research assistant now for 6 semesters, so ever since the spring of my freshman year, I've been doing it. Dr. Noble was the leader and kind of got me into that whole realm, so I have him to thank for that. But that experience started doing coal scrubber dust research, so coal dust scrubbing research. And I saw that project from the very start of it through prototyping and creating kind of a contraption to capture coal dust, all the way to this past spring when I was out in Phoenix, Arizona at the Society of Mining and Metallurgical Engineers conference there. I saw the PhD student, Assad, present that project in front of a room of people. So it was a great full circle moment for me to see something that I helped work on as a freshman to then as a junior going and seeing it in front of all these people as a real full-scale project. It was a really, really great experience. And through the undergraduate research, I've just met so many people, industry partners, professors, and other students, PhD students, master, undergraduate students, and connected with them, shared ideas, and just learned so much through all that experience.
Okay, we'll pass it to ISC.
To restate the question, what was the neatest aspect of your undergraduate experience that you have taken advantage of? For me, this is really getting involved in, sorry about that, getting involved anyway in school within Virginia Tech. So there are a lot of different professional organizations you can get involved in, which I would really stress early on in your undergraduate career to get involved with those societies so you can network with upperclassmen, and there's lots of opportunities to travel through some of these professional organizations. For me, I've traveled to the Women Engineering Conference with the Society of Women Engineers. It's the largest women engineering conference in the world, and through that conference I've gotten multiple internship opportunities, and you can meet so many like-minded and different-minded individuals in the field. And I would just say get involved, because there's so many wonderful people here for you to meet at your time in Virginia Tech. So just get involved in whatever way you can and just try out different things. That is probably the best thing that you can do. And for me has been the coolest part of my undergraduate experience.
The neatest part of my undergrad experience has definitely got to be the design teams that I got an opportunity to be a part of. That was definitely up there on the slides. I was on DBF, Design Build Fly, for 3 years, and I joined that as a freshman. I basically said, I have no idea what kind of major I want to be. I'm a general engineering major. I think planes are cool. I know nothing. What can you teach me? And that was enough to get going, and for them to start teaching me in a bunch of different disciplines and taking advantage of the scale and resources that Virginia Tech had and supporting teams like DBF allowed me to progress not just as an engineer, but also just as it applied to my career. Taking advantage of design teams, regardless of which major you go into. Almost all of them, to my knowledge, have design teams. Find one, go talk to them. They were at Gobbler Fest. They're probably going to be willing to talk to anyone even after Gobbler Fest. Join a design team. It is the greatest way that I can say to probably get experience early on. It can also help you decide your major. So for me, DBF helped me eventually go between, like, oh man, what do I want to do? Mechanical, electrical. I was still between that, biomedical, aerospace, and I was like, you know what? I like it enough here, and it definitely worked out. I got to be a lead my sophomore and my junior year, and that was definitely one of the most fun experiences that I got to do. You obviously got to be working with friends all the time as you go through and complete your own engineering project, and you always will have faculty and departmental support in doing so.
Excellent. Okay, let's move on to our next question then. As students are trying to determine the best program for them or the best major, what is one piece of advice that you would give to them to help make that decision? And let's start with you at this table here at Aerospace and Ocean Engineering.
Okay, I have a really short, easy answer for that. And that is, think about what you want to do for your capstone design, and then figure out which major offers that kind of project, and then go with that major. Because everything that you learn before you go to capstone design is going to prepare you for capstone design. So you're going to enjoy what you're doing, assuming you're going to enjoy your capstone design. Thank you.
Dr. Noble already mentioned this, but think about what kind of problems you want to solve. Think about how you go about solving problems and kind of what realm you want to be in. And then once you've narrowed down to a couple majors, I'd say to help make your decision where you want to land as an engineer, join the clubs, join the design teams, go to the conferences. Those are the people that you'll be with for the next 3 years. Do your best to get to know them, ask the upperclassmen what they think, talk to the professors. Don't be shy. Get out there, really ask them the true opinion, and go from there.
Yeah, I want to add and address this a little bit differently. This is actually a concept we cover in my sophomore leadership course. And what it is, you know, through the process of self-discovery, you should think a lot about what your core values are. And this is something I didn't really look at in a serious manner myself until I was a working professional. And it's something I wish I had done when I was a student. And really think deeply, like at your core essence, what drives you and what you really value in life. And if you can find a major and a career that has alignment with your core values, that's where you're going to be most effective and have the most satisfaction for your entire life. So I would encourage you all, as you think about what you want to do and what you want to major in, I would start that conversation by deeply thinking about what do you really value.
So for determining the best major for you, I think it's really important to really look at all the majors. When I came in as a freshman, I had my heart set on computer science. I was like, that is the only thing I will major in, and if I'm not doing that, then I'm not doing anything else. And now you can tell I'm not a computer science major, so I would really look at all the major options for you. You could think that there's one thing that this is what you want to do for the rest of your life. And once you start taking a couple more classes in that, you could think, oh, maybe I want to try something else out. And try that out. Do a design team. Go talk to students in that major. There are so many people here willing to help you and want to help you find what you want to do with your time in undergrad and post-grad. So really take the time to learn about the different majors. As a freshman, I did not know what industrial and systems engineering was, and now I could not imagine myself doing anything else. It really is a perfect major for me. So really just look at all the majors and see what you can do with those post-grad. Look at the research opportunities within these departments, and just kind of take the time to think and be open-minded.
That's great. I love everybody's answers to this question across the whole table. And I will just give one additional piece of advice that I would say that I think could fit for whatever major you're exploring. And because I think if you reach out to any of the advisors, whether the freshman advisors, they can help connect you with us in departments, or just reach out to us in the departments. But I really think that one thing I would also suggest, in addition to everything everyone else said, is try to talk to some alumni, maybe alumni a year out, 2 years out, maybe 5 years out, to really understand what do they do with their degree. Like, what's a day in the life like? What kind of job title do you have? Who else in your company do you work with closely? Is it all other mechanicals or all other industrial engineers? Like in our case as ISCs, it's almost never that you're working on project teams with just a bunch of other ISCs. You're often, the ISC bringing the toolkit to many other projects. So we have a young alumni board. We call it the Emerging Leaders Board of alums that are 15 years or less out from graduation. And then we have an Emerging Leaders Network. Between those two, that's like 50 volunteers that are ready to go at the snap of a finger. I just send them an email, hey, there's a student that wants to help get a little interviewing. Can you do a mock interview with them? And they're like on it in a day. So there would be a very easy way, at least in our department, and I'm sure it would be true in others as well, that they can help connect you to a few alums, maybe kind of younger alums, so you can understand what like a day in the life is like and how they feel like they're using their degree.
All right, excellent. Thank you all so much for being here tonight. I think that's about all the time we have for the Q&A. And what I would like to do is have you all give all of our panelists a round of applause. And you all are free to exit the stage whenever you'd like. They're going to pull the screen back down. And then for all of you that are here for the Foundations of Engineering class assignment, in just a few moments after they pull the screen down, we will have the QR code. Do not leave this space, though, until you do fill out the survey so that you make sure that that is captured for your class attendance. And if you do have questions, or if you all need your tablecloths for the tables out there, feel free to grab them as well. If you have questions that you want to ask after we're done, you'll be able to ask those up there in the atrium area. And so it'll take just a few more minutes because you'll have to come back downstairs and open the shutter. And don't tackle our friends trying to get to their tables. Let them get out there and get their tables staffed. So we have one more evening of Explore Engineering. That's tomorrow evening here from 5 to 7 o'clock here in Burris Auditorium. So those of you who this is your first night, I look forward to seeing you tomorrow afternoon. All right, thank you all very much for being here tonight. Take your time though, make sure you get this QR code, make sure you do the survey before you leave the space.